Hello, this video is changing systems, and before we begin, two masses are sitting on a table and they're connected by a string here. The string's right here. And the friction between the table and the masses are going to be negligible, so we're going to take those out of the problems right away. And what I want you to do is to draw a box around two different systems here. Because I'm going to tell you that one of the important things that you need to understand in physics, especially for the AP exam, is that you need to understand that having two different systems can help you solve the same problem. In fact, in many cases, you need more than one system to see what's going on, to see not only the big picture, but the intricate parts that make up that picture. Okay, so here's the first system. I went ahead and drew a box around both masses and said, okay, I'm going to treat both of these guys as an object. Or I can change it around and say, well, my system 2 is here, and I can treat the first mass as an object. Or I could just draw a box around the third one over here and call that system 3, and draw a box around that one and treat that one as an object. Okay. So today what we're going to do is we're going to solve dynamics problems by changing from one system to another to show you that you really can't solve a problem sometimes with just one system. You have to change things around a little bit and see it from different ways. So let's go back to this problem, but now let's go ahead and add a question to it. So we've got these two masses, they're on the string, they're connected, and there's no friction between the masses in the table. A force is applied to the right, force applied, of mass 2, and the two masses accelerate. I want you to calculate the tension in the string between the two masses in terms of the force, mass 1 and mass 2. So here's my string in between the two boxes here. Okay, so we've already created a system here, and now I'm going to treat my system as an object. Okay, I can just draw a point particle there and then sum all the masses acting in the x direction. And when I do that, it's the mass of the system. So it's the sum of all forces in the x direction is equal to the mass of the system, which is both masses, times acceleration in the x direction, which is equal to the force applied to them. Notice there's no other mass. There's tension, it's right here, but it's not it's in the system, but it's not a part of the system that I want to create that's going to show me tension. So what I have to do in this problem, there's no tension in the equation here, is I have to change my system. You have to. And notice what happens when I do that. So now I'm going to go ahead and treat my mass 1 only as a system, system 2, and I can draw free body diagrams for this. And from here, I've got mass of 1, and I can go ahead and sum all the forces in the x direction is equal to the mass of the first one, because that's my system, times the acceleration in the x direction, and that's going to be equal to the tension right here. It's the only force being applied to this system. And if we take a look here, we'll notice that in both systems, they've got an acceleration, and they're going to accelerate at the same rate because it's a part of the same problem here. So what I'm going to do is I'm going to go over here to this equation here and solve for the acceleration. And when I do that, I get the force applied divided by the mass 1 plus mass 2. And I can go ahead and take that acceleration and plug it in here. And when I do that, I get the equation here. Now, what I can do also, and this is big for the AP, is they ask, well, what's the relationship between the force applied and the tension? Well, in this particular case, we can say that, well, these three masses are going to be constant, and we can say that the tension is going to be proportional to 1/3 of the force applied, and that would be our answer. So again, as always, I always want you to encourage you to solve for the variables first. Do not put any numbers, and even if the question asks for numbers. Then once you solve for the variables, then you can see the relationships between those variables. Let's take a look at another example here. So I got two masses, they're attached to a pulley system with a rope, okay, over here. And as always in these problems, you always want to assume that the mass of the rope is negligible. In other words, it's massless. And the friction in the pulleys are negligible, or there is no friction in the pulleys. That's what we do in these problems to simplify them. Okay, let's go with our first system. I'm going to go ahead and treat both masses as a system. Draw my free body diagram, and if you don't remember how to do that, this is a very familiar problem, because it looks like that modified, it looks like that Atwood machine that we've done before in previous videos. So if I move them to horizontally, then I can say, well, the weight of the second one is going to pull it in the positive direction. The weight of the first one is going to pull it in the negative direction. And because it's the same mass for both, we're going to assume it's an equilibrium. So the sum of all forces is equal to 0, which is equal to the weight of the second one minus the weight of the first one. And if I take this weight and put it over here, well, that's an obvious statement. The weight of the second one is equal to the weight of the first one. Well, that is the obvious point here, because each mass is 80 newtons. However, that's not what we're trying to do here. We're trying to change the system around to see if we can come up with the answer, because I'm looking for some sort of tension, and I don't see it in any in this equation here. So let's change the system. Okay, there it is, system 2. Now let's do our free body diagram. We'll see that our tension is going positive. The weight of the first one is going negative. From there, the sum of all forces is equal to the tension minus the weight. And when I solve this problem, I get an answer of 80 newtons. I'm going to tell you that when I first saw this problem, and when many of my students see this problem, it's a natural tendency to say, well, wait a minute, it's 160 newtons, because I've got 80 newtons pulling down this way and 80 newtons pulling down that way. Well, that's not entirely correct. It's actually equal to the weight of both of them individually. And the only way to really understand that is to break it up into two different systems, system 1 and system 2, and then from there, solve the problem. All right. So if you have any questions, or if you need tutoring in Phoenix, go ahead and give me an email at monroe.watson@gmail.com. Thank you.